Learning objectives. In this chapter, the users would learn the following aspects of soldering techniques. Inspection of populated PCB board. Post-drilling inspection. A wealth of information is available by simply examining the materials from the drilled stack and the drill bits. For instance, inspecting the drill bits will allow one to determine if wear occurs at consistent rates or will reveal whether hit count maximums are excessive and the type of drill hole wall defects to expect. Bonded debris and/or extensive wear to the drill corners imply high drilling temperatures or materials that are not fully cured and point to a problem with the materials or may suggest an excessive surface speed. Extensive primary cutting edge wear indicates abrasive materials and may require lowering stack heights, reducing hit counts, or replacing entry or backup materials. Post-drilling inspection continued. Burrs on the surfaces within the stack means that there is a problem with the way panels are assembled and pinned, or it may be the result of warped panels. Entry or exit burrs on the outer laminates should cause one to question the entry or backup materials or the in-feed rate. The point of post-drilling inspection process is that if one takes time on a regular basis to examine materials and drill bits after drilling, many drilling problems would be solved before they get out of hand. Soldering. Soldering is a process in which two or more metal items are joined together by melting and flowing a filler metal, solder, into the joint. The filler metals have a lower melting point than the adjoining metal. Soldering differs from welding in that soldering does not involve melting the workpieces. In brazing, the filler metal melts at a higher temperature, but the workpiece metal does not melt. In the past, nearly all solders contained lead, but environmental concerns have increasingly dictated use of lead-free alloys for electronics and plumbing purposes. Applications. Soldering is used in plumbing, electronics, and metalworking, from flashing to jewelry. Soldering provides reasonably permanent but reversible connections between copper pipes in plumbing systems, as well as joints in sheet metal objects such as food cans, roof flashing, rain gutters, and automobile radiators. Jewelry components, machine tools, and some refrigeration and plumbing components are often assembled and repaired by high-temperature silver soldering process. Small mechanical parts are often soldered or brazed as well. Soldering is also used to join lead came and copper foil in stained glass work. It can also be used as a semi-permanent patch for leak in a container or cooking vessel. Electronic soldering connects electrical wiring and electronic components to printed circuit boards, PCBs. Types of solders. Most of the solder metals are the alloys of tin and lead. These alloys exhibit a wide range of melting points, so different type of soldering metal can be used for a variety of applications. Percentage of lead is kept low due to its toxic properties. Tin becomes chemically active at soldering temperature and promotes a wetting action required for making the joint. Copper, silver, and antimony are also used in soldering metal as per the strength requirements of the joint. Different solder metals have different melting points and varying applications. Types of solders continued. A solder is selected on the basis of its melting point. If metals to be joined have high melting point, solder of high melting point is generally selected. Solder of high melting point provides better strength of the joint. Inner layer inspection of multi-layer boards. Inner layers of multi-layer boards can shift during fabrication processes and create poor layer-to-layer alignment. During the artwork exposure or fabrication of the multi-layer boards, the position of the copper shifts relative to the nominal stacked position. This can create breakout or missing of the copper pads when drilling the interconnection holes. Two methods of inspecting the inner layers of multi-layer panels exist. One that has been used for several years is X-ray. This technology has progressed significantly and is widely used. X-ray. X-ray technology is used to inspect the inner layers of multi-layer PCBs and to verify that the drill pads are located properly. Inner layer shift is identified easily in an X-ray image, and a simple technique can be used to measure the misalignment accurately. In developing the PCB artwork, a set of stacked pads are located in the coupon area. These are inspected and a best fit centering is calculated. X-ray inspection also is used to determine movement of each individual layer. In this case, a locating pad with a corresponding layer pad is on each individual layer. The system can measure the distance from the locating pad to a layer pad and determine movement of each layer due to the location of the layer pads. PCBs can be inspected after tooling holes are drilled to verify that they are in the proper locations. In addition, X-ray inspection can be performed after final drilling to verify that the holes are centered within the pads. Types of soldering fluxes. Soldering fluxes can be classified as organic and inorganic fluxes. Organic fluxes. Organic fluxes are either rosin or water-soluble materials. Rosin used for fluxes are wood gum and other rosin which are not water-soluble. Organic fluxes are mostly used for electrical and electronic circuit making. These are chemically unstable at elevated temperature but non-corrosive at room temperature. Inorganic fluxes. Inorganic fluxes consist of inorganic acids, mixture of metal chlorides. These are used to achieve rapid and active fluxing where formation of oxide films is a problem. Soldering fluxes. Fluxes should be removed after soldering either by washing with water or by chemical soldering solvents. The main functions performed by fluxes are remove oxide films and tarnish from base part surfaces, prevent oxidation during heating, and promote wetting of the faying surfaces. The fluxes should be molten at soldering temperature, be readily displaced by the molten solder during the process, and leave a residue that is non-corrosive and non-conductive. Soldering process. There are three forms of soldering, each requiring progressively higher temperatures and producing an increasingly stronger joint strength. Soft soldering, which originally used a tin lead alloy as a filler metal. Silver soldering, which uses an alloy containing silver. Brazing, which uses brass alloy for the filler. The alloy of the filler metal for each type of soldering can be adjusted to modify the melting temperature of the filler. Soldering differs from gluing significantly in that the filler metals alloy with the workpiece at the junction to form a gas and liquid tight bond. Soft soldering is characterized by having a metal point of the filler metal below approximately 400 degrees Celsius or 750 degrees Fahrenheit, whereas silver soldering and brazing use higher temperatures, typically requiring a flame or carbon arc torch to achieve the melting of the filler. Soft solder filler metals are typically alloys that have liquidous temperatures below 350 degrees Celsius. In this soldering process, heat is applied to the parts to be joined, causing the solder to melt and to bond to the workpieces in an alloying process called wetting. In stranded wire, the solder is drawn up into the wire by capillary action in a process called wicking. Capillary action also takes place when the workpieces are very close together or touching. The joint's tensile strength is dependent on the filler metal used. Soldering produces electrically conductive, water and gas-tight joints. Each type of solder offers advantages and disadvantages. Soft solder is so called because of the soft lead that is primarily its ingredient. Soft soldering uses the lowest temperatures but does not make a strong joint and is unsuitable for mechanical load-bearing applications. It is also unsuitable for high-temperature applications as it softens and melts. Silver soldering, as used by jewelers, machinists, and in some plumbing applications, require the use of a torch or other high-temperature source and is much stronger than soft soldering. Brazing provides the strongest joint but also requires the hottest temperatures to melt the filler metal, requiring a torch or other high-temperature source and darkened goggles to protect the eyes from the bright light produced by the white-hot work. It is often used to repair cast-iron objects, wrought iron furniture, etc. Soldering operations can be performed with hand tools, one joint at a time, on a production line. Hand soldering is typically performed with a soldering iron, soldering gun or a torch, or occasionally a hot air pencil. Sheet metal work was traditionally done with soldering coppers directly heated by a flame, with sufficient stored heat in the mass of the soldering copper to complete a joint. Torches or electrically heated soldering irons are more convenient. All soldered joints require the same elements of cleaning of the metal parts to be joined, fitting up the joint, heating the parts, applying flux, applying the filler, removing heat and holding the assembly still until the filler metal has completely solidified. Depending on the nature of flux material used, cleaning of the joints may be required after they have cooled. Each alloy has characteristics that work best for certain applications, notably strength and conductivity, and each type of solder and alloy has different melting temperatures. The term silver solder likewise denotes the type of solder that is used. Some soft solders are silver-bearing alloys used to solder silver-plated items. Lead-based solders should not be used on precious metals because the lead dissolves the metal and disfigures it. Soldering and bracing process. The distinction between soldering and bracing is based on the melting temperature of the filler alloy. A temperature of 450 degrees Celsius is usually used as a practical delineating point between soldering and bracing. Soft soldering can be done with a heated iron, whereas the other methods require high-temperature torch or furnace to melt the filler metal. Different equipment is usually required since a soldering iron cannot achieve high enough temperatures for hard soldering or bracing. Brazing filler metal is stronger than silver solder, which is stronger than lead-based soft solder. Brazing solders are formulated primarily for strength. Silver solder is used by jewelers to protect the precious metal and by machinists and refrigeration technicians for its tensile strength but lower melting temperature than brazing, and the primary benefit of soft solder is a low temperature. Since the joint is produced using a metal with a lower melting temperature than the workpiece, the joint will weaken as the ambient temperature approaches the melting point of the filler metal. For that reason, the higher temperature processes produce joints which are effective at high temperatures. Brace connections can be as strong or nearly as strong as the parts they connect, even at elevated temperatures. Optical inspection. Optical inspection has been discussed elsewhere. It is generally applied early in the fabrication process as a yield improvement and data collection tool, not as a means of final product qualification. However, with improvements in resolution, the type of defects that may escape undetected becomes somewhat more limited, and optical inspection is argued as a possible means of final testing. With complex multi-layer product, optical inspection will not be able to identify assembly, contamination-induced defects internal to the board in any case, and may still be limited in cases of contaminants or very fine geometry shots and opens on external layers. The equipment is somewhat slower than universal grid test systems, particularly when run at very high resolution. For such reasons, it is still not common practice to employ optical inspection by itself as a substitute for electrical testing. This may be a method that develops further in the future or that finds acceptance in special circumstances. Inspection under UV light. To verify complete coverage and touch-up. Coatings contain a fluorescent dye that will glow under UV light and show where the coating has or has not been applied. Areas without coating can be touched up at this time. The areas most susceptible to insufficient coating are corners of parts where the coating can flow away and leave little behind, the protruding ends of through-hole part leads, and the shadowed areas under or behind larger components. If large flat areas are uncoated and show beads of coating, there is a wetting problem due to improper surface preparation or a material incompatibility. Inspection under UV light continued. The coating should also be inspected for improper thickness, bubbles, trapped material, or debris, and incomplete curing. Mask material should be removed carefully. To prevent peeling, it may be desirable to score or cut the coating at the edge of the mask so that the coating tears along the correct line. Ensure that the mask is removed entirely and that no residue has been left behind on the board. Latex mask that has been overheated will be sticky and difficult to remove completely, as will overheated masking tapes. Soldering methods. There is a lot of similarity between soldering processes. The different processes or methods used in soldering are touch soldering, furnace soldering, resistance soldering, dip soldering, and infrared soldering. These may apply to hand soldering, wave soldering, and reflow soldering. Hand soldering. Hand soldering is done manually using solder iron. Small joints are made this way in very short duration of approximately 1 second. Wave soldering. Wave soldering is a mechanical technique that allows multiple lead wires to be soldered to a printed circuit board as it passes over a wave of molten solder. In this process, a PCB on which electronic components have been placed with their lead wires extending through the holes in the board is loaded onto a conveyor for transport through the wave soldering equipment. The conveyor supports a PCB on its sides, so its underside is exposed to the processing steps, which consists of the following. Flux is applied through foaming, spraying, brushing, and wave soldering is used to pump liquid solder from a molten bath onto the bottom of board to make soldering connections between lead wire and metal circuit on the board. Reflow soldering. This process is also widely used in electronics to assemble surface mount components to print circuit boards. In this process, a solder paste consisting of solder powders in a flux binder is applied to spots on the board where electrical contacts are to be made between surface mount components and the copper circuit. The components are placed on the paste spots and the board is heated to melt the solder, forming mechanical and electrical bonds between the component leads and the copper on the circuit boards. Inspection and testing. There are various types of connector inspection: PCA inspection, solder silver inspection, electrical testing, and tool check. Connector inspection. Check the connector after pressing for even bottom side pin protrusion, top side connector body seating height, damage to the connector body, inaccurate mating pin positions within the connector as opposed to within the board, damage or movement of electrical shields if the connector is so equipped. PCA inspection. Check the PCA for surface damage in the area of the pressing operation. A mispositioned or damaged press tool or board support can damage components or overly compress the laminate, causing outer or inner layer trace damage. Look for errant tooling marks on the PWB surface after the press fitting operation. Overcompression of the board can lead to compressed or severed traces within the board. A compressed trace may impact current capacity and result in localized circuit overheating or otherwise impact signal integrity. Solder silver inspection. Check the bottom side of the board for solder silver formation. This is especially relevant in the case of HASL, hot air solder leveling boards. Brush these out if required and inspect. Loose slivers may cause electrical shorting on the board or other boards within the system enclosure. Work with the PWB vendor to ensure that drilled and plated holes are sized appropriately for the press fit process and that excess solder from the HASL process does not adversely alter the finished hole size or shape. Electrical testing. In the case of high-friction surface finishes, such as OSP, Organic Solderability Preservative, copper, forces applied during the press-fit process may be so great as to cause damage to the PTH, plated through-hole barrel, or adjacent inner or outer layer circuit traces. Check the board visually and by electrical test as part of the first article inspection. Check tooling frequently. Check for excessive tool wear or damage. A damaged tool can ruin a connector or PWB and replicate the damage over many boards. Soldering tools. The main tool used for soldering is a soldering iron. In addition to soldering iron, some consumables are also used in the process of soldering, like fluxes, solder wire, or stick and spelter. Soldering iron. It consists of a copper bit attached to iron rod at its one end and a wooden handle at the other. It is used to melt the filler metal and paste it to make the joint. A soldering iron can be a forged soldering iron, which is heated in a furnace to have sufficient temperature to melt the filler metal, or it can be electric solder iron. Electric solder iron is heated by passing electric current through it. Use of electric solder iron is popular and cost-effective. It is used in making very precise joints in electronic and electrical equipment. Spelter. Spelter is an alloy of zinc and copper in equal proportion. This is one of the filler metals with low melting point with other desirable properties to make good quality solder joint. Different types of solders and fluxes, which are common consumables used in soldering, have already been described. Some precautions are to be followed to keep the soldering tools as described. Selection of correct tool according to the process. A defective tool should not be used. Electrically heated solder iron should have proper earthing. Hot solder iron, when idle, should be placed on its proper stand. Tip of the solder iron should be cleaned before its use. Solder iron should be gripped at its handle while in use. Desoldering and resoldering. Used solder contains some of the dissolved base metals and is unsuitable for reuse in making new joints. Once the solder's capacity for the base metal has been achieved, it will no longer properly bond with the base metal, usually resulting in a brittle, cold solder joint with a crystalline appearance. It is good practice to remove solder from a joint prior to resoldering. Desoldering braids or vacuum desoldering equipment, solder suckers, can be used. Desoldering wicks contain plenty of flux that will lift the contamination from the copper trace and any device leads that are present. This will leave a bright, shiny, clean junction to be resoldered. The lower melting point of solder means it can be melted away from the base metal, leaving it mostly intact, though the outer layer will be tinned with solder. Flux will remain, which can easily be removed by abrasive or chemical processes. This tinned layer will allow solder to flow into a new joint, resulting in a new joint, as well as making the new solder flow very quickly and easily. Lead-free electronic defects. More recently, environmental legislation has specifically targeted the wide use of lead in the electronics industry. The ROH's Restriction of Hazardous Substances directives in Europe require many new electronic circuit boards to be lead-free by 1st July 2006, mostly in the consumer goods industry, but in some others as well. In Japan, lead was phased out prior to legislation by manufacturers due to the additional expense in recycling products containing lead. However, even without the presence of lead, soldering can release fumes that are harmful and are toxic to humans. It is highly recommended to use a device that can remove the fumes from the work area either by ventilating outside or filtering the air. It is a common misconception that lead-free soldering requires higher soldering temperatures than lead-tin solder. The wetting temperature in lead-tin solder is higher than the melting point and is a controlling factor. Wave soldering can proceed at the same temperature as previous lead-tin soldering. Nevertheless, many new technical challenges have arisen with this new endeavor. To reduce the melting point of tin-based solder alloys, various new alloys have to be researched with additives of copper, silver, bismuth as typical minor additives to reduce melting point and control other properties. Additionally, tin is a more corrosive metal and can eventually lead to the failure of solder baths, etc. Lead-free construction has also extended to components, pins, and connectors. Most of these pins use copper frames and either lead, tin, gold, or other finishes. Tin finishes are the most popular of lead-free finishes. Nevertheless, this brings up the issue of how to deal with tin whiskers. The current movement brings the electronic industry back to the problem solved in the 1960s by adding lead. JEDEC has created a classification system to help lead-free electronic manufacturers to decide what provisions to take against whiskers depending upon their application. Soldering defects. In the joining of copper tube, failure to properly heat and fill a joint may lead to a void being formed. This is usually a result of improper placement of the flame. If the heat of the flame is not directed at the back of the fitting cup and the solder wire applied at 180 degrees angle opposite the frame, then solder will quickly fill the opening of the fitting, trapping some flux inside the joint. This bubble of trapped flux is a void, an area inside a soldered joint where solder is unable to completely fill the fittings cup because flux has become sealed inside the joint, preventing solder from occupying that space. Soldering procedure. Following sequential steps should be carried out as soldering procedure. Workpieces which are to be joined together should be perfectly clean. There should not be any dirt, dust, rust, paint, or grease. This is so that the solder or spelt can stick to the joint with proper strength. Cleaning is done with the help of a file or sandpaper. In case of joining of conducting wires, insulation of portion to be joined should be perfectly removed. Sometimes chemicals are used to clean the workpieces. Descaling is done by dipping the workpieces in dilute hydrochloric acid. Soldering procedures continued. Preparation of joint. After cleaning, workpieces should be kept together in correct position to make the final joint. Workpieces should be clamped to avoid any relative movement between them that may disturb the joint making. At the joint, small grooves are made on the workpieces to facilitate better flow of molten solder and so good strength of the joint. There are two objectives of joint: to bear load and to make electrical contact. In case of load-bearing joints, lap joint or butt joints are preferred. It is important to note that the strength of a soldered joint cannot be compared with welded joint. If electrical contact is to be made, the solder should be so selected that resistance of joint should match with the resistance of the conductor. Fluxing. Fluxing includes selection of appropriate flux and its application to the joint. Selection of flux depends on the material of workpiece, keeping its purpose in view. It is applied to the joint with the help of a soldering brush before soldering. It avoids oxidation of molten metal, helps in flow of molten solder into the joint, and so maintains strength of the joint. Inspection categories. There are 4 types of inspection categories. They are material inspection, qualification inspection, quality conformance inspection, and reliability testing. Material inspection. This inspection usually consists of certifications from the material supplier, supported by data from the supplier's own inspections. The materials used must be inspected by the PCB manufacturer to ensure compliance with customer requirements. Qualification inspection. The PCB supplier must provide proof to the user of its qualifications to build the product specified. The user must then review this proof in order to minimize the risk associated with buying from the PCB manufacturer. This process usually includes a PCB manufacturer supplying a self-declaration of capability such as those found in the IPC 1710 and then supplying some kind of physical sample or testing data to support the assertions made in the self-declaration. It is up to the PCB user to determine the level and detail of qualification required. Quality conformance inspection. These product verification inspections use specified acceptability criteria and are performed prior to shipment of PCBs to customers. These inspections can be defined either by industry or customer standards or by a combination of both. Reliability testing. This testing consists of looking for imperfections in the PCB that may show up at some time during the product's field life. They include accelerated life testing for both the interconnection and insulation attributes of the PCB. Soldering defects and their remedies. Some of the common soldering defects are discussed below. Granular formation at the surface of the joint of solder is one of the common soldering defects. Formation of spheroids at the surface of soldering joint is also a similar defect. This happens due to underheating or overheating of soldering iron, insufficient use of flux. Formation of spheroids makes the joint ugly and weak in strength. Improper or uneven application of flux may make the joint of weak strength. Proper coordination between flux application and soldering makes the joint of good quality. Safety precautions in soldering. Keep the solder iron always on its stand. All electrically operated instruments and equipment should have proper earthing. Sometimes emission of smoke during soldering operation may become poisonous due to a particular type of flux. Operators should have protection from the same. Flux should be applied gradually while soldering. While diluting HCl, water should not be added to HCl, but HCl should be mixed into the water drop by drop to avoid accidents. Workplace should have enough ventilation and smoking should be strictly prohibited during the operation. Workplace should have the facility of first aid. It should be noted that good quality surface preparation always contributes to good quality joint. Electronics. Various problems may arise in the soldering process which leads to joints which are non-functional either immediately or after a period of use. The most common defect when hand soldering results from the parts being joined not exceeding the solder's liquidus temperature, resulting in a cold solder joint. This is usually the result of the soldering iron being used to heat the solder directly rather than the parts themselves. Properly done, the iron heats the parts to be connected, which in turn melts the solder, guaranteeing adequate heat in the joint parts for thorough wetting. In electronic hand soldering, the flux is embedded in the solder. Therefore, heating the solder may cause the flux to evaporate before it cleans the surfaces being soldered. A cold solder joint may not conduct at all, or may conduct only intermittently. Cold solder joints also happen in mass production and are a common cause of equipment which passes testing, but malfunctions after some years of operation. A dry joint occurs when the cooling solder is moved and often occurs because the joint moves when the soldering iron is removed from the joint. Soldering types and features. Soldering methods are broadly divided into two types, the partial heating method and the total heating method. Partial heating method. Heat is applied to the package leads and/or PWB, printed wiring board, in a localized manner. Types. There are 4 types of soldering methods: using soldering iron, hot air, laser, and pulse heating. Features. Partial heating involves less heat stress on the device and printed wiring board, but is unsuitable for large volume production. Therefore, this method is mainly used to correct soldering or for devices with a low heat resistance. Total heating method. Heat is applied to the entire package and/or PWB. Types. There are various types of soldering methods such as infrared reflow, convection reflow, infrared convection combined, VPS, vapor phase soldering, and flow wave soldering. Features. Because of excellence in productivity and running cost, the total heating method is widely used. However, this method can place considerable heat stress on the semiconductor device and board. Inspection criteria. When inspecting PCBs, the requirements can be separated into externally observable attributes and internally observable attributes. The actual requirements vary by specification, but the requirements stated generally follow IPC document guidelines. Tools. Hand soldering tools widely used for electronic work include the electric soldering iron, which can be fitted with a variety of tips ranging from blunt to very fine, to chisel heads for hot cutting plastics rather than soldering. The simplest irons do not have temperature regulation. Small irons rapidly cool when used to solder, say a metal chassis, while large irons have tips too cumbersome for working on PCBs and similar fine work. Temperature control irons have a reserve of power and can maintain temperature over a wide range of work. The soldering gun heats faster but has a larger and heavier body. Gas-powered irons using a catalytic tip to heat a bit without flame are used for portable applications. Hot air guns and pencils allow rework of component packages which cannot easily be performed with electric irons and guns. For non-electronic applications, soldering torches use a flame rather than a soldering tip to heat solder. Soldering torches are often powered by butane and are available in sizes ranging from very small butane oxygen units suitable for very fine but high-temperature jewelry work to full-size oxy-fuel torches suitable for much larger work such as copper piping. Common multi-purpose propane torches, the same kind used for heat stripping paint and thawing pipes, can be used for soldering pipes and other fairly large objects, either with or without a soldering tip attachment. Pipes are generally soldered with a torch by directly applying the open flame. A soldering copper is a tool with a large copper head and a long handle, which is heated in a blacksmith's forge fire and is used to apply heat to a sheet metal for soldering. Typical soldering coppers have heads weighing between 1 and 4 pounds. The head provides a large thermal mass to store enough heat for soldering large areas before needing reheating in the fire. The larger the head, the longer the working time. Historically, soldering coppers were standard tools used in auto bodywork, although body solder has been mostly superseded by spot welding for mechanical connection and non-metallic fillers for contouring. Toaster ovens and handheld infrared lights have been used by hobbyists to replicate production soldering processes on a much smaller scale. Bristle brushes are usually used to apply plumbing paste flux. For electronic work, flux core solder is generally used, but additional flux may be used from a flux pen or dispensed from a small bottle with a syringe-like needle. Wire brush, wire wool, and emery cloth are commonly used to prepare plumbing joints for connection. Electronic joints are usually made between surfaces that have been tinned and rarely require mechanical cleaning. Though tarnished component leads and copper traces with a dark layer of oxide passivation, as on a new prototyping board that has been on the shelf for about a year or more, may need to be mechanically cleaned. A heat sink, such as a crocodile clip, can be used to prevent damaging heat-sensitive components while hand soldering. The heat sink limits the temperature of the component body by absorbing and dissipating heat, reducing the thermal resistance between the component and the air, while the thermal resistance of the leads maintains the temperature difference between the part of the leads being soldered and the component body, so that the leads become hot enough to melt the solder, while the component body remains cooler. Reason for inspection. Manufacturers inspect printed circuit assemblies during production for a variety of reasons. Most of these reasons fall into the following categories. Improvement of process defect coverage. Improvement in ability to meet customer specifications. Detection of process defects as quickly as possible after they occur. Ability to decrease process defect rates through statistical process control. Automated inspection. The automation of inspection has evolved into systems that resemble the automated test equipment used to make electrical measurements and find electrical defects. Automated inspection systems generate images of the item to be inspected, digitally analyze the image to locate and measure key features, and based on these measurements, automatically decide whether a defect exists or not. Automated inspection continued. Just like visual inspection, automated inspection systems do not require physical contact with the printed circuit assembly to generate the desired images. Unlike visual inspection, however, automated inspection removes human subjectivity from defect detection, thereby increasing repeatability rates, typically by an order of magnitude. Many of the automated inspection systems also provide accurate, repeatable, quantitative measurements that directly correspond to process parameters, thus providing the means for process control and improvement. Conclusion. In this chapter, the users have covered the following aspects of soldering techniques. Inspection of populated PCB board.